Okay, so different problem, same strategy. Let's see if we can evaluate this and come up with anything interesting. So let's see, we got when x of pi halves equals 0. Okay, so we're going to plug in, so 0 equals c1 cosine of pi halves plus c2 sine of pi halves. In the event that you are a little rusty on your unit circle, pi halves is right up here, and it's got an ordered pair of 1, 0. So it's got a a sine of 0 and a cosine value of 1. So that's actually backwards. So 0, 1. Whoops. Wow, good thing I'm the teacher, right? Okay, so what that says is with that initial condition, I have the equation 0 equals, and that piece is equal to 0. So that says C2 times 1. Okay, so C2 equals 0. Okay, so that tells me that I essentially don't have to worry about C2, but let's use that other fact, the derivative fact. So if x is C1 cosine t plus C2 sine t, then what would x prime look like? Well, x prime would be derivative of cosine is negative sine, so negative C1 sine t plus C2 cosine t. And then we want to evaluate that. So that says, let's see, 1. And then I'm going to put a pi half in here again. So sine of pi halves plus C2 cosine of pi halves. All right, well that goes to 0 here. And let's see, so that says 1 equals negative C1 times 1. So C1 has to be negative 1. All right, so let's put those two facts together. And so our general equation would be x equals negative cosine t. So that would be the only thing that satisfies that. All right, determine by inspection at least two solutions of the given first order initial value problem. So determine by inspection is a fancy way of saying just guess some stuff and see, you know, what could you just guess and check and come up with something. So we don't have you do a lot of something like this. I mean, we know, you know, we got constants, so we can maybe start with y equals 0, y equals 1, y equals 2. Maybe we do something like x, and then x squared, and then x cubed. Maybe we try trig, and we go with cosine, sine, something like that. Or maybe we even look at e to the x and see if any of these tend to satisfy this. Hopefully we'll come across pretty quick and go, oh, nope, doesn't seem to work pretty good. So let's try y equals 0 real quick. So y equals 0 would be y prime is also 0. So if I put that into both sides, I get x times 0 equals 2 times 0, which is true. Okay. So I know that is a potential solution. What about a different constant? Could I try y equals 1? So y equals 1 and then y prime would be 0. So that would be x times 0 equals 2 times 1. And that doesn't work. Okay, so as far as the constant family goes, I kind of ran out of other potentials. What about y equals x? Okay. So y prime is equal to 1. So x times 1 equals 2 times x. Okay, that didn't work. So I know that's not going to be a good idea. But maybe we'll try a different exponent. So x squared. So 2x. Sorry, I should probably put little lines here indicating when I've got different ones. Alright, so let's try that one. So x times 2x, is that equal 2 times x squared? And it does. Okay. So we got a second solution here. What about cosine? So y prime would be negative sine t. So that would be x. And I realize I should probably stick these with x's. So cosine x and sine x. So x negative sine x equals 2 cosine x. I don't think that's going to work out for us. Yeah, no, that's not going to work out. Okay, so that's not worthwhile to check. So if cosine didn't work, sine doesn't look like it's going to work, and I'm trying to think of how the trig identities work. I don't think the trig identities would pan out for us. I mean, we have two solutions, so I've answered the question, but I kind of started this exploration, so let's keep going here. Y prime would also be e to the x, and so x times e to the x equals 2 times e to the x. And that's not going to work. Not e to the x itself. Maybe throw a constant in there. Maybe we'll luck out. Maybe did 2 e to the x. But I think you'll find that that's not going to pan out for us, because that's going to be 2 times 2x. Yeah, so that's not going to work out. So e to the x isn't going to work. So it looks like our two solutions for this particular one are y equals 0 and then x squared. And I believe if we, just for kicks and giggles, let's keep going with this. Let's see, what if y is x cubed? So y prime would be 3x squared. So x times 3x squared, does that equal 2x cubed? And the answer is no. What about x to the fourth? Y is 4x cubed, or y prime is 4x cubed. X times 4x cubed, 2x to the fourth. Okay, so that's not going to work either. So it turns out the only two spots we get this is at specifically y equals 0 and then x squared. And I bet if we threw other constants in there, maybe we could play around with that. But we found two solutions. All right, determine whether the following differential equation possesses a unique solution through the given point. Okay, so this is asking us to think about that rectangular theorem where we were looking at the function and its derivative and identifying domain restrictions dealing with that. So if we say f of xy is equal to the square root of y squared minus 9, what about f prime of xy? Okay, so I'm going to rewrite this to the 1/2 power. Okay, so the derivative would be 1/2 y squared minus 9 to the negative 1/2, and then our chain rule would be 2y. And so I'm going to rewrite that. That would be y over the square root of y squared minus 9. Okay, so any domain restrictions we're looking at for our uniqueness would be essentially determined by that derivative, and specifically the square root of y squared minus 9. So I want to make sure that y squared minus 9 stays positive. show y squared is greater than 9, so then y would have to be greater than 3 and less than negative 3. So we kind of think about it in a number line here. If I do anything inside, so anything in this interval here, that would actually violate domain restrictions, so I just need to make sure it's actually outside of this. And it's, let's see, I want to make sure it's parentheses and not a radical there. So as long as I've got something smaller than negative 3 or something bigger than infinity, or bigger than positive 3, then I would have some form of a unique solution that does exist in that interval. So in the interval 1 to 4, there is a piece of that, specifically from 3 to 4, that would guarantee unique solutions. So yeah, there does exist a unique solution within that interval. So there you go.